Hey, today we're happy to have Ryutaro Matsudo, who's going to tell us about the missing final state puzzle in the monopole-fermion scattering.
Yes, thank you very much for the introduction. Today I'd like to talk about the process of the monopole-fermion scattering. This work is based on this paper in collaboration with Ryuichiro Kitano. Let's consider where there is a gut monopole, and according to the Rubakov and Galland, when proton collides with the gut monopole, it decays into a positron and mesons. And this effect is important for searching the gut monopole. Actually, the effect has been used to put constraint on the monopole flux in the universe. Let's see the origin of this effect. Let's consider the massless QED with one flavor of Dirac fermion. When the left-handed positively charged fermion collides with a monopole, it has happened that the helicity flip of this fermion. This helicity flip happens even in the massless QED. The only possible source of this Heberian number violation is the Chiral anomaly. And as the effect of this anomaly, there appears the fermion condensate around the monopole. Here R is the distance from the monopole. Then as a consequence, this kind of helicity flip happens in one flavor case. However, when we consider two flavors of massless Dirac fermion, there arises a puzzle. In this case, due to the conservation of the flavor charge, there are no candidate of the final state of this scattering. It means that the helicity has to flip. However, there are no such state with the correct flavor charge in this case.
Isn't it the case that there's no single particle state, but there could be a multi-particle state?
Even if the multi-particle state, there are no candidate. Later, I'd like to explain in more detail. Actually, there are no candidate over the final state. However, in this talk, I'd like to solve this puzzle by identifying this final state as Pancake's soliton. That is the soliton of the phase of the fermion condensate. This is our consequence of the work. Yeah, this is the outline of my talk. Firstly, I'd like to explain the missing final state puzzle in more detail. And in the second part, I'd like to review S-wave approximation of the theory. This is a useful technique for calculating this scattering process. And as a result of this calculation, we obtain some mysterious final state of this scattering process. And I'd like to explain this. And in the third part, I'd like to explain the Pancake soliton, and I'd like to identify this soliton as the final state of this scattering process. And in the fourth part, using this soliton, I'd like to show some soliton picture of the scattering process of fermion and monopole. Now let's start with the missing final state puzzle. The origin of this puzzle is the helicity flip property of the scattering of monopole and positively or negatively charged fermion. This helicity flip occurs in the QED. This phenomenon can be explained in semi-classically as follows. If there is a monopole and a charge, actually electromagnetic field carries additional angular momentum as this. Here, this is the usual expression of the angular momentum carried by the electromagnetic field, and by substituting the usual Coulomb electric field and the magnetic field carried by monopole, then we obtain this expression. Here, this R hat naught is the unit vector pointing from the monopole to the charge. This figure shows this situation. This M is the monopole, and this is the positively charged particle. Then this is the unit vector pointing from monopole to charge. Then the electromagnetic field have this kind of angular momentum. And we consider positively charged fermion comes into collides with monopole with the collides with monopole. Then we consider this incoming particle has a helicity minus 1/2. In this case, the total angular momentum is 0. The sum of this and this is 0, then we can say that the total angular momentum is 0. Then we consider this scattering. Then after this scattering, the situation can be described as this figure. In this case, the direction of the unit vector can be written as this. Then the angular momentum for carried by electromagnetic field can be written as this. The direction becomes opposite. Then, in order to maintain the total angular momentum to be 0, the helicity of this fermion has to flip. This is the explanation of the helicity flip. So we can say that helicity has to flip in this scattering. So next, to see the puzzle in more detail, we consider a specific theory of and we actually consider an SU2 gauge theory with an joint Higgs and 4 flavors of bifermions.
Sorry, can I ask a naive question? So
Yeah, yes.
I don't work on this, so I'm very naive. But it looks like this argument that you just gave would say that the scattering amplitude vanishes in the forward limit. But you're trying, because that's really where you have exactly the angular momentum in the electromagnetic field gives you delta J equals 1, right? But
yeah.
But you're trying to say something about the S wave, but it's not really obvious to me that you can build up the S wave out of this forward scattering. So could you, it's not obvious to me what this delta J, how to think about this delta J when I'm talking about forward scattering.
delta J means that
I mean, and somehow an S wave, the R naught averages to 0. That's all I'm saying.
in quantum mechanics, we can say that this actually S wave state can be written as just a spherically symmetric field, but this picture is some a classical picture. So in this sense, but anyway, yeah, we can say that the total angular momentum is 0. But
I guess I'm supposed to think of the,
It's not the wave
the
function of the
electromagnetic,
particle.
the
It's
electromagnetic contribution to the angular momentum. I should think of that as being associated with the scattering particle. And then I'm somehow supposed to add it to the other angular momenta in the problem. Is that the way you do it quantum mechanically?
it's an S wave of the total angular momentum.
Yeah, and this JEM is really associated with the incoming particle.
this JEM carried by the electromagnetic field, so
Right,
what you're
Actually,
saying, Marcus, is that the
but
initial
R naught
state
points
is not a product of two one-particle states, because there's
this state is actually the in some sense two-particle state.
okay.
Because there is a monopole. So if we consider this monopole as a background field, in this sense we can consider this is one particle state. But in general, this is a two-particle state. So
Yeah. Okay, go ahead. I think I can follow. Thank you.
Okay. Let's specify the theory. We consider SU2 gauge theory with joint with one adjoint fix and 4 flavors of one fermion, and we consider because of we consider that SU2 is spontaneously broken down to U1, and then because of this breaking, we obtain the two-fifth magnetic two-fifth Fourier magnetic monopole. And important point is that the global symmetry of this theory is SU4. Here, these are the fermion contents of this theory. Here, A and B is consists of SU2 doublet, and there are 4 SU2 doublets, and these 4 fermions consist of the SU4 quadruplet. This is the contents of Y fermion. Then this theory actually can be regarded as an approximation of SU5 GATT. And if we regard this as an approximation of SU5 GATT, the standard model fermions can be identified as this. Here, A1 is AL plus, EL plus, and B1 is DL3. Here 3 is denotes the color degrees of freedom, and so on. Then in this talk, I approximate this SU2 theory as the gauge theory of unbroken U1. So in this approximation, we consider only these 3 types of field. Yeah, A is the U1 gauge field. this AJ is a wire fermion with charge +1, and BJ is wire fermion with charge -1. And the dot Dirac of monopole is approximated by the background Dirac monopole. And other XY bosons and Guth-Higgs boson are considered to be infinitely heavy, and we just neglect these contents. I'd like to explain the missing final state puzzle in this setting. And these are the fermions in this theory, and this denotes the quantum number of fermion. Here, AJ is a left-handed particle, and this has a positive charge, and it belongs to the fundamental representation of SE4. And other wire fermion can have the quantum numbers as this. Then we consider the scattering of AJ and Dirac monopole. In this case, as we see in the previous slide, the helicity of this state has to flip. So the final state should have a quantum number as R+1 and the fundamental representation. However, in these fermion contents, there are no particles with this quantum number. So in this sense, there are no corresponding particle. Actually, in the calculation of S-wave approximation, we obtain the final state as some mysterious state. We can write this state as this kind of state. Here, this Pj over 2 denotes the state with halves of U1 charge, the flavor charge, and the spin of Bj. So this V1 over 2 has the 1/2 of charge and 1/2 of flavor charge, and spin 1/2 of 1/2. So but however, it is hard to interpret this kind of state. So
doesn't that just tell you that the S-wave approximation fails in this case?
No, this interpretation is hard, but actually the S-wave approximation, I direct claim that the S-wave calculation is correct, but there are no interpretation of this state.
How do you quantify how big a contribution could you get from non-S-wave?
So actually, I'd like to claim that the no important effect from other higher partial wave.
So you're saying the S-wave is exact?
Yes, not exact, but it is enough to consider this scattering using S-wave approximation.
You can always project onto the S-wave, why not?
Well, if the final state has zero overlap with the S-wave, then you won't find the final state.
No, but if the initial state is S-wave, the final state has to be S-wave.
Yes.
S-wave of some total angular momentum, not
total angular momentum.
Particle wave functions. This is restricting to S-wave of individual particle wave functions now.
Yes. So in this sense, actually higher partial wave can affect the process, but it's suppressed in.
Suppressed by what?
actually the it may suppressed by the okay it's higher loop effect. It could be the higher loop effect. So
I mean, when Callan introduced this, it was just a guess, right? He hoped that it would work, but he didn't have any reason to know why the things he's dropping was just a truncation, not an approximation, in the sense of there's a small parameter that we're expanding in. He just truncated the states of a field theory.
Actually, it's the truncation. So yeah, actually, actually yes. So this is some truncation, but yeah, actually, it can be said that just hope, but
why do you continue with your talk?
Can I ask a question? What does the half from the flavor charge means? They are fundamental and anti-fundamental representation. How do I see that they combine to a fundamental representation?
Yes, but in some sense, this halfway means that the charge of corresponding to the maximal torus of SE4. So there are no clear meaning, but in some sense, we can say that the charge corresponding to maximal torus of SE4.
You want this combination to be a fundamental representation, right? As you said, how do I see that they combine into a fundamental representation of SU4?
So 3 anti-fundamentals make a fundamental, and then you have half of a fundamental from the 3 anti-fundamentals and half a fundamental from the fundamental.
I see.
But you can see from that you could make a final state from 3 anti-fundamentals, right? That would be a sensible final state. Not these particular anti-fundamentals, but some combination of anti-fundamentals.
Yes. This one is actually specific 2, 3, 4. So a specific component of the anti-fundamental in the anti-fundamental representation.
But the combination that would work is not in a particle S1. So why do you go on with your talk?
Okay. Let's it's okay to. So let me go on to the next slide. This actually there are no interpretation of this state. However, someone claims that this can be interpreted as follows. In the SU5 gut, the particles can the standard model particle can correspond as this. Then the Hamilton state can be written as this. The Callan claims that this semitone state can be interpreted as this state. This means that the superposition of ER and this combination. However, this interpretation is problematic. This is because once we observe this particular ER plus, then the flavor charge conservation is just violated because this ER plus is in the anti-fundamental representation with E4. So, in this sense, this interpretation is problematic. So, and if massless QED is unitary, and there must be, in this sense, we can say that there must be a final state of this scattering process. So, in this sense, we need to interpret this kind of state. And we will see that the non-perturbative effect of QED can make this final state, can make this state appropriate. Now, I'd like to review the S-wave approximation of the state of this scattering process, and we will see that how to obtain the state with such semitone final state. This S-wave approximation of the theory is performed as follows. First, this is the theory in the 4D spacetime, and by substituting the spherically symmetric fields of gauge fields and the fermion field, we obtain the 2D theory. That is the Schwinger model. Then we can apply the bosonization technique to the 2D theory. Then we obtain this theory. Here we integrated out the gauge field by adapting the Gauss law constraint. Then we obtain this Coulomb interaction term, and this is the kinetic term for the scalar field. And R is the distance from the monopole. And then in this theory, the fermions correspond to the kink soliton. Kink means that the for example, phi 1 changes from 0 to 2 pi. This is a kink. Then the kinks, in general, kinks correspond to fermion with the charge plus 1. So this is, for example, this phi 1, the kink for phi 1 is A1. And the anti-kink, that is the jump from corresponding to the jump from 0 to minus 2 pi. Then this corresponds to the negatively charged particle. And another important point is the incoming kink always corresponding to A or A bar, and the outgoing kink always corresponding to B bar or B. And in the 4D picture, this kink can be written as this spherically symmetric thing. And this corresponds to just a S-wave state of fermion. Then these expressions are the currents of U1 and the maximal torus of SU4. This is the U1 current. and these three are the current corresponding to maximal torus of SU4. And this means that the current of U1 generated by diagonal matrix of this. And the boundary condition is important. The boundary condition is determined so that any charge does not flow into the infinitesimal region around the monopole. This condition prohibits the existence of the diode. And actually, we can write this condition as this. Then we obtain these boundary conditions of the scalar field. These four conditions of using this boundary condition and the equation motion, we can calculate the scattering process. Now we consider the initial state is A1. This corresponds to the kink of phi 1. It jumps from 0 to 2 pi. And according to the calculation, if when it reaches the origin, then in order to maintain the boundary conditions, the values of phi 2 or phi 3 and phi 4 changes as this. Here, when x reaches the pi, the change of at the origin stops, then there remains this kind of object. And there appears the half kink. Here, phi 1 jumps from pi to pi, and phi 2 jumps from pi to 0, and so on. So there appears the half kink. And this, we don't know, we didn't know the interpretation of this state, but we can write this as this. And actually, this state has the correct charges using, we can confirm this has the correct charge by using this formula. But we don't know what actually this is. For comparison, I'd like to consider the massive case. If the fermion has mass, this puzzle disappears. Let's see how this puzzle disappears. Now we consider the this kind of mass term. Then in this, when we introduce this mass term, the global symmetry reduces to the U1 times U1 that is generated by these two diagonal elements. And they are not, the charge corresponding to this this matrix is not conserved when the mass term is introduced. In this case, they are candidates of the final state. For example, A1 has the quantum number as this. Here the charge of corresponding to this is 1 and this is 0. The final state must have the must have quantum number as this. Here, this has to be right-handed, and we have the particle with this quantum number that is B2 bar. Then in this case, there is a candidate of the final state. Actually, according to the numerical simulation by the Darson and Shalekens, we can confirm actually this kind of final state is obtained. According to this numerical simulation, first we, after the scattering, first we obtain this kind of semitone-like state. However, then it collapses in as this, then we obtain final state as this. This corresponding just a dB bar. So in this sense, we can say that yeah, if we add mass, then we just obtain the V2 bar. That was the final state. So in this sense, what I'd like to explain what happens when we take the massless limit. In the S-wave calculation, we see that when semitone reaches this R equal to has the similar value to 1 over m, then there appears another wall from the core of the monopole. Then it reaches the semitone state. Then we obtain the V2 bar. This means that in the region, in this region, we can say the theory can be approximated by the massless theory. In this sense, if we take massless limit, this region wraps all the space-time, then we can say that in the massless limit, every point is near the monopole. The massless limit can be taken as this. And then next, I'd like to explain the final state of this S-wave approximation. How to interpret this the final state using the soliton. In the S-wave calculation approximation, the final state is described as a soliton in the bosonized theory. So you want to interpret this soliton, the picture, the bosonized picture in 4D is useful. And the theory is actually the effective theory of the phases of fermion condensates. We know the fact that in the monopole background, these kind of operators of fermions have non-zero expectation value. This is the origin of the helicity flip in this scattering. Then we obtain the effective theory for the phases of these operators by integrating in the phases and integrate out the fermion fields. The variables of the effective theory can actually the following 4 variables. The theta A denotes the phase of this operator, and the theta 1j is the phase of this operator. And the other phases can be written as a linear combination of these 4 variables. And it is convenient to express these phases using the phase of the fermion field. Let alpha j be the phase of AJ and Bj be that of Bj. This means that if the change of phase of A1 corresponds to just the shift of alpha. Here, important point is that this alpha and beta is 2 pi periodic. This is because if theta is 2 pi, this transformation is unity. So in this sense, we has to this alpha 1 has to be equivalent to alpha 1 plus 2 pi. Then this alpha is 2 pi periodic. And these genuine variables can be expressed using this alpha and beta as this. And another important point is that there are configurations of alpha j and beta j that represent an identical configuration of phases of condensate. So the expression using alpha and beta is actually redundant expression. And next we consider using this variable. We can construct the this kind of configuration. This is we call the pancake. And later I'd like to confirm this can actually describe the fermion. And this object is actually a 2+1 dimensional object.
How do you get that from, you started with fields that had spherical symmetry?
Here we don't assume that the spherical symmetric field. We just consider.
But your semitons have spherical symmetry.
Actually, in this consideration, we don't assume that the spherical symmetry.
So you have to throw out the S-wave approximation because it can't give you a pancake.
Later, I'd like to identify the semiton as semiton as the S-wave state of the soliton state. So in this consideration, we don't assume the spherical symmetry.
So you're just not going to use the semiton solutions from now on.
I don't use the semiton solution. Yes, I will not use.
Okay.
Okay. We just consider for the theory of the fermion condense, the phase of fermion condensate. Here, this object is corresponds to this kind of object. This is the slice of this object, and on the bulk of this object, the value of alpha j changes from 0 to 2 pi. This means that at the and this alpha j equal to 2 pi is equivalent to the alpha j equal to 0. Then in other regions, alpha j is fixed. And this means that the around the boundary, alpha j changes from 0 to 2 pi. This means that alpha j winds this boundary. And now I'd like to consider the effective theory of the phases of fermion. Due to the chiral anomaly, if we shift the phase of AJ, then we obtain this phase of the this shift of the Lagrangian. And also in the same way, we obtain this kind of shift. And to reproduce this feature of the theory, in the effective theory, we this kind of term has to be introduced. Here, when alpha j changes theta, this change is reproduced. So we need this term in the effective theory. And we can read off the U1 current from this expression by taking the variation of the gauge field. Then we we obtain this expression of the U1 current. And using this expression, we obtain the we can say that some object have the pancake object have the charge. Before proceeding to consider the pancake object, let's consider this kind of object. This means that here monopoles are lit by the wall of alpha 1. Here on the wall, alpha 1 changes from 0 to pi. Then by substituting the field strength of the Dirac monopole, we obtain this expression. Here, this is the charge of the object. Then we obtain this expression. Then by integrating with, by substituting this change of alpha 1, then we obtain this. Then we can say that this kind of object have a charge 1. And actually, this just spherically, if this configuration is spherically symmetric, this just corresponds to the kink of in the SF theory. And and we can consider this wall have a boundary. And actually, if this wall have boundary, this is just the pancake introduced in the previous slide. And in this, if there is a boundary, actually there are edge modes on the boundary. And the addition of the contribution from written effect and the edge contribution, we can obtain, we can say that this object have the charge 1. Let's see this in more detail in the next slide. And now we consider the effect, the theory on the wall of the phase of the fermion condensate. By substituting the 2 pi jump over alpha j into this term of in the effective Lagrangian, we obtain the Chern-Simon theory on the wall. Here, this obtained by integrating by part over this f. Then
is A the gauge field?
Yes, this A is gauge field and F is the field strength corresponding to this A. A is the U1 gauge field. U1 gauge field. Then the CS theory is not gauge invariant when the wall have the boundary. So in order to maintain the gauge invariance, we need chiral edge mode on the boundary. Actually, this is the theory, the total theory. Here, there appears the chiral edge mode on the boundary. Thanks to this phi f term, the gauge invariance is maintained. Here, the phi, the A gauge transforms as this, and at the same time, phi gauge transforms as this. Then this expression is the covariant derivative of phi. And another important point is that this scalar field of phi on the edge is a 2 pi periodic scalar. And then this because of this, we can define the winding number around the edge of phi as this. This takes the value this is actually integer valued. Then we will see that the pancake with excited edge state with the winding number plus minus 1 can be considered as a fermion. To see this, we determine the expression of charge in this theory in the next slide. This is the
what's the energy of the pancake? Is it a finite energy soliton?
This is actually finite energy soliton.
So does it grow with the size of the pancake?
But actually, we don't know the full theory of the effective theory, so we don't calculate the energy of this kind of object. Actually, we can't calculate the energy, but just we can say that this object corresponds to the fermion just by the correspondence. Just in the original theory, we know that there is a fermion, so if we construct the object with the same quantum number, we can identify them.
Well, you already constructed all the fermions with the spheres. So it seems like you already have all the fermions, and now you have another fermion that corresponds to the pancake.
Yeah. We will see that actually this object has actually the correct quantum numbers. So we just claim that because of this correspondence of the quantum numbers, we can say that it should be regarded as the fermion. So so in this sense, we just say that this pancake object corresponds to fermion just by identifying the quantum numbers. So yeah, so sorry. Sorry, what is the question of
These are just some new fermions in addition to all the fermions we had before.
The pancake, actually this pancake object contains new and original fermions. Actually, it contains original fermions.
The last sentence, do you mean the pancake with excited age state or
Yeah.
excited?
Excited state means that just phi equals 0 is ground state, and excited mean.
Okay, yeah, just to check, it's a typo, right? Existed. Excited.
Excited, yes. This is typo.
So this pancake is the wall with a hole. Is that what I mean?
Yes. This wall is hole,
Okay.
and okay. Okay. Let's move. Let's consider the U1 charge of this object. Here, here's the expression with the U1 charge. This is obtained by just by variating the U1 gauge field. Then there are two contributions. First one is H contribution. There appears the winding number, and this expression is a gauge invariant, and this is the contribution from bulk, and this is just the contribution from the Witten effect. And in the gauge where the Dirac string does not penetrate the pancake, this contribution from A and F just cancels. This is because by adapting the Stokes theorem, this contribution from A and F cancels, then we obtain, we can just say that this charge is represented using the winding number of phi around the edge. And
what would you get if it went through the Stokes, through the pancake?
Here, sorry.
What charge would you get if the string went through the pancake?
When a Dirac string, when the Dirac string penetrates these full expression is gauge invariant, so the total charge does not change. So if in the gauge where the Dirac string penetrates the pancake, the contribution from d phi changes to the contribution from A in that case. And in that case, we cannot use the Stokes theorem, then the contribution from A and F is not cancelled. Is it okay?
Yeah.
Okay. Then the then we can say that the when the winding number phi has a winding number, it has the U1 charge. Then we can say that the excited state with winding number 1 has charge 1. This eigenstate of the winding number can corresponds to the solution of equation motion. Actually, if we neglect the gauge contribution from the gauge field, we can write this kind of solution as this. And actually, here L is the length of the boundary of the pancake. Then actually we can confirm that this, when we substitute this into this, we obtain 1. Then the state corresponding to this solution have the charge 1. And by introducing the background gauge fields of maximal torus of SU4, we can repeat the similar argument as this, then we can confirm that actually if this phi have winding number 1, then the object have the also have the flavor charge corresponding to the fundamental representation of SE4. Then we can say that if this H state have winding number 1, the object have charge 1 and flavor charge corresponding to the fundamental representation.
What energy does this state have?
It's actually the energy can only calculated the contribution from the energy of coming from each state can be calculated, but it depends on the explicit form of the theory. Here, there, we have
Just from this, you have this integral over the boundary. In that effective theory, what's the energy?
Actually, the energy depends on this V. Here, this V is as a constant. As a constant, and in this sense, we cannot determine the energy because there is unfixed constant.
But what is it as a function of V?
Actually, it's proportional to V.
Okay.
Then okay, this object have the charge and flavor charge. And next, I'd like to consider this object to actually have spin or not. Then the spin of the object corresponding to the generator of translation along the edge. Because the translation along the edge corresponds to just a rotation around the axis perpendicular to the pancake, then it just corresponds to the spin in this direction. Then we can write the spin as this. And by substituting the solution of in the theory, we obtain this. Then we can say that this object have the spin 1/2. And the important point is that direction of the spin depends only on the orientation of the wall and does not depend on the charge. So if the charge depends on this plus minus sign of phi, but in both cases, the obtained spin is just 1/2. Then the direction is fixed as this. Then this pancake object have the charge and the flavor charge and the spin 1/2. Then we can say that this is the fermion. Actually, for example, we can consider this kind of pancake. Here, alpha j changes from 0 to 2 pi. And then the direction of the spin as this. Now we consider this pancake travels in the direction this direction denoted by this double arrow. Then we can say that this object have the helicity, the left-handed helicity. Then we can say that the quantum number of this object is the same as AJ. Then we can identify this as AJ. Then on the other hand, we can also consider this pancake object travels in the opposite direction. In this case, this object have the chirality, the R-handed helicity, right-handed helicities. Then there are no corresponding fermion in the original theory, original Lagrangian. So we can say that this pancake is actually the new fermion. Then this object have just opposite helicity. Then the final state of the monopole-fermion scattering can be identified this object. This is our claim. So the pancake can describe
this non-perturbative pancake moving one direction reproduces the perturbative degrees of freedom. And when it moves the other direction, it's some new degrees of freedom.
It's just the non-perturbative thing of.
But how does it, on the left, it's reproducing the perturbative degrees of freedom.
We already integrated out the fermion field, so the theory can contain any of the state. For example,
when did we integrate out the fermions?
In the first place. To obtain the effective theory of the phases, we integrated in the phases of these operators and integrated out the fermion fields. But this is just we cannot actually calculate this path integral, but we imagine that we can perform these integration.
So originally, the reason why there was this distinction about incoming and outgoing was because of the monopole.
Actually, here
so this looks like, I don't know, is it independent of the magnetic field of the monopole?
This we only assume that there is a monopole at some place, so this the direction does not depend on this. The existence of this pancake does not depend on where is the monopole.
So it's not moving towards or away from the monopole. That doesn't matter.
Yeah. Later, I'd like to consider the scattering process using this fermion, and we can see that we can consider using this object to consider the scattering process, but we don't see any contradiction with the S-wave calculation. So in this sense, it's okay. there are no problem. Actually, even if B particle travels into the monopole, the total angular momentum is not zero. So in this sense, it is consistent. Is it okay? Or
Yeah, let's continue.
okay. Now let us consider the massive case. And in the massive case, there are no puzzle, and this kind of new fermion should disappear. But let's see how it happens. Now we consider this kind of master. Then in this case, the global symmetry reduces to the U1 times U1. Then we can write corresponding to these two generators. Then in this case, there are only two flavor charges. Then we cannot distinguish the B2 bar and this new fermion, formerly new fermion. And this the pancake with travels that travels in the opposite direction have the same quantum number as B2 bar. In this sense, we cannot distinguish B2 bar and this pancake object. So in the massive case, all of the pancake corresponding to the original fermions. So there are no new state in this case. So next, I'd like to see the a scattering process of using this pancake soliton. To consider the scattering process, the boundary condition is important. The boundary condition it can be written as this. This boundary condition is obtained has to be imposed for the action to be finite. Because at the origin, the gauge field, the field strength diverges. So at the origin, this object, this quantity has to be zero. And also, if we introduce the background gauge field of SU4, then the similar boundary condition is obtained. Due to these boundary conditions, we can say that if alpha 1 changes from 0 to 2 pi at the core of the monopole, then in order to maintain these boundary conditions, beta j changes as this. Then using this, we can consider the scattering process of pancake and monopole. Now we consider the pancake of alpha 1 goes to the monopole. Here, this corresponds to the fermion of A1. And if it reaches the monopole, the place of monopole, then because of the boundary condition, the values of beta changes as this. Then there appears this red wall, but however, this red ball corresponds to just transparent. This means that there is no object actually. This is because under this change alpha 1 0 to this value, the genuine variables does not change. So in this sense, there are no object here. So then after travels this this pancake goes to left, then there remains the monopole back of this kind of monopole back, and this monopole back have the charge +1. Then for the because of the conservation of the charge, this object does not have the charge, and then this pancake can disappear because this does not have any charge. Then this monopole back can break as this by poking the hole on the wall. Then there remains this kind of object. Here, this object is just the new fermion with opposite helicity. This is the process of the scattering using this soliton picture. Then next, I'd like to consider the massive case.
Before you do that, what happens to this fermion when it gets infinitely far away?
This fermion just remains. So in the massless case, this is the final state.
So shouldn't perturbation theory work far from the monopole?
Part of it. The existence of this object is just from the non-perturbativity effect, so we can not use
So what is the non-perturbative effect infinitely far from the monopole?
Actually, in the massless case, there are no distance scale, so we cannot separate the place near the monopole and the place.
No, there are wavelengths, right? That I send in the particle with a definite wavelength, so there's a scale.
A wave
Has some
wavelength
momentum and energies.
Okay, but
you said the condensates fall like 1/r². That must, or 1/r to the n, that has a scale in it too.
Yeah. But the energy but okay, but we can say for example, if we consider the massive case, then we can say that the distance is the 1/n distance from the monopole. As I said in the S-wave calculation, in the this region we can consider the theory as massless theory. In this sense, the scattering fluorescence does not so depend on the energy of the initial state. So irrespective of the energy of the initial state, we can say that in the region we can consider this theory is massless. In this sense, if we take the massless limit, all of the point we can say that the theory is massless. In the similar sense, we can say that there's no okay. The existence of the pancake object does not depend on the scattering process. This existence is just the consequence of the existence of a magnetic monopole. So it does not. We cannot. It is not necessary to consider the scattering, but if we place the monopole at some point, then there appears this kind of object. So in this sense, there are no distance scale.
So if I had an SU5 gut and there was one monopole in the universe,
yeah,
then I would see additional particles in addition to the quarks and leptons in the gut.
If the fermions are massless. But there is a distance scale. Yeah, in the gut, there is a distance scale coming from the QCD, so we cannot say that this new kind of object, a new kind of object appears. So
if neutrinos were massless, then guts would be ruled out. But because they have a small mass, they're not ruled out. That's
but in the this constellation can only be adapted to all of the fermions are massless and they are SU4 global symmetry. So in this sense, we cannot adapt it to SU5 gut. In the SU5 gut, if we regard this SU2 theory as an approximation of SU5 gut, the standard model particles are corresponding to these this kind of.
So if I send in a positron, what is your prediction of what comes out?
So in the gut, SU5 gut, so there are quarks, so there is a distance scale. So
yeah, take the massive case. What's the final state?
If we neglect the SU3 gauge theory and we take the massless limit, there appears new fermions.
In the massive case.
In the massive case, there.
What's the final state?
When the massive case and we neglect the confinement, the effect of confinement, if we A1 particle, just helicity flip occurs. So
pardon, what?
A1 goes to AB bar, A to B bar, so this means EL to ER plus. when we neglect the confinement, the effect of confinement.
Okay, let's move on. We should try to wrap up soon.
Okay, this is a scattering process. Then next view, I'd like to consider the massive case. In this case, in the massive case, the region corresponding to these variables is no longer the vacuum. This is because there appears additional condensate. This M is actually mass of the fermion. Then there appears these kind of condensates. Then by change these configuration is no longer changes the values of these condensates, then we can say that this configuration is no longer the vacuum. Then this red shaded region is no longer the vacuum. Then when this region becomes large enough, then there appears another wall from the monopole. Here, inside of this wall is the vacuum. Then this wall emerges with the outer wall. Then there remains this kind of object. Then this reaches this pancake. Then there remains this object. This just corresponds to B2 bar. So this is just original fermion. This is the case of massive case. I'd like to summarize my talk. When the charged fermion collides with the monopole, the helicity of the S-wave component of the fermion has to flip, irrespective of what the UV theory is. The only possible source of this flip is the chiral anomaly. This means that when there is a monopole, the effect of the anomaly is not suppressed in QED. As a consequence, there is a fermion condensate violating the fermion number conservation. However, if we consider two or more flavors of massless direct fermions, there appears puzzle that any fermion cannot be the final state of the monopole-fermion scattering due to the flavor charge conservation. We solve this puzzle by identifying the final state as the new fermion. That is the soliton of the fermion condensates in the monopole background. Thank you for your attention.
Let's unmute. So questions from someone else?
This is kind of a weird question. Is there an analog of this problem in 2 dimensions? Can we have a monopole in 2 dimensions? There, you sort of understand the anomaly and everything in a much extremely concrete way. Has anybody looked at that?
2-dimensional.
Well, that's what this S-wave
S-wave
approximation is. It's a 2D theory.
Yeah.
Yes. But I mean, there you can solve the whole theory, right? There's no approximation. It's not an approximation anymore. And a lot of things you can solve exactly in 2D.
Yeah. In the S-wave theory, when the fermion is massless, we can solve the theory exactly. And
so then it should be able to solve the 2D theory.
Exactly. Yeah, Callan did. There's the solution.
Yeah. In the S-wave theory,
you can have half a fermion in 2D. That's the solution.
Yeah. In the S-wave theory, actually this kind of soliton is actually exist.
Right. Yeah, that's what I mean, that's all I guess I'm really saying. It looks like, but on the other hand, you have to be a lot more careful about the IR in 2D, right?
No.
Anyway,
When
it's just
when that soliton goes out to infinite distance, doesn't it have infinite energy? Because isn't the vacua are at 0 and 2 pi, and pi is a maximum of the potential, isn't it?
Vacuum? What?
The vacuum solutions are 0 and 2 pi. That's why there's a kink. So when you say the solution is that it sits at pi, then it's sitting at the maximum of the potential.
When we add the mass term, it's just a
no, but in the massless case.
In the massless case, this is just a solution. So no contribution from the it's just a vacuum. This pi and minus pi is just vacuum.
Let me see. Do you mean that in the massless case, if when there is a monopole, you just double the fermion spectrum?
Yes.
And these doubled fermions are exactly these semitons?
Yes.
But the semitons were spherically symmetric, and the pancake could not have spherical symmetry.
This symmetry is spherical symmetric, but the pancake is not.
Yeah, I'm confused why you say you can identify the semitons with the pancakes. They have different symmetry.
If we the object of this this kind of monopole back just we consider that just corresponds to the kink in the S-wave theory. And the pancake is obtained by just poking the hole of in this hole.
Yeah, I'm asking what's the correspondence of the pancake in the
pancake is obtained
in the S-wave theory. What is the pancake?
In the S-wave theory, we don't have pancakes.
Okay, so then they're not semitons.
The S-wave state of the pancake can be described as this kind of monopole back. We consider that the S-wave state of the pancake can be described as.
But those are just the ordinary kinks.
This just corresponds to the usual kink. And in the 4D theory, we can consider this object can have the boundary.
So I guess it sounds to me like you're saying the S-wave theory is wrong because the final state is just a single fermion. Whereas in the S-wave theory, it was 4 half fermions.
But this interpretation is just wrong. But this interpretation is wrong. But this object just corresponds to the monopole back of in the 4D theory. Then it can be considered as the S-wave state of the pancake soliton in our claim.
Any other questions?
John, what's your solution? I thought you are working on that too. Is there a...
Well, I mean, you can preserve the SU4 symmetry if there's three anti-fundamentals in the final state. And you can conserve angular momentum if they're not, the individual particles are not S waves.
Oh, in the SF theory, in my understanding, these one of the semiton is not corresponding to the state. And yeah, all this combination of these things is just the new state of fermion.
Any other questions? Let's thank Ryutaro again.
Thank you very much.